Hi, this is Jeff Kerner, Business Unit Manager for Richardson Electronics. And on behalf of Richardson Electronics and United Silicon Carbide, I'd like to welcome everyone to today's webinar, 5 Design Tips for Easy Silicon Carbide Implementation. Your presenter today will be Dr. Zhangde Li, Senior Staff, R&D Engineering at United Silicon Carbide. Throughout the presentation, Mr. Li will provide important links to additional technical content which support designing the United Silicon Carbide FETs, and we will provide webinar attendees with a copy of the presentation and a follow-up email. Finally, at the end of today's webinar, we will cover important technical FAQs. If you have a specific question, please send them to sales@unitedsiliconcarbide.com, and the team of United Silicon Carbide Power Experts will respond. Zhangde, take it away.
All right. So today I would like to give you 5 design tips. And so let's look at what might be the situations that the power designers might be facing today. So the first scenario might be you already have your silicon-based design, and you just need to boost its power or efficiency. So what you might be looking for is a drop-in replacement silicon carbide FET that works with your existing silicon-based design, mainly the gate drive. You might be using silicon MOSFET or IGBT. The second scenario might be you already made a decision to do a whole new design with silicon carbide FETs, and you're looking for a safe transition from silicon MOSFET or IGBT to a silicon carbide FET-based design. And the third scenario might be you already have a silicon carbide-based design, but you need an alternative silicon carbide FET. So what you need is this FET has to work with your existing silicon carbide-based gate drive, and it has to achieve the same or better performance. So that leads us to the 5 design tips I would like to give you today. The first one is silicon carbide FET gate drive guidelines. Second is about using the silicon carbide FET body diode. And the third is silicon carbide FET technology comparisons. And after that, I would like to show a few cases where and how you can use silicon carbide FETs. And the fifth is what to do if you want to upgrade your existing design with a drop-in replacement solution. Okay, so first, let's look at the gate drive. So here is the figure comparing the silicon and the silicon carbide gate drive. So for the silicon MOSFET and IGBT, because their typical threshold is about 5 volts, as a result, usually they do not require negative gate drive, so you can drive it from 0 volts or turn off. And the FET is usually fully on with VGS of about plus 12 volts. Now, the conventional silicon carbide MOSFET, the threshold is lower. It's usually about 2.5 volts. And as a result, typically they require minus 5 volt threshold to make sure the device stays off. And another thing is, to achieve the lowest possible RDS on, it is required to drive the VGS to plus 15 to 20 volts. And for comparison, UnitedSiC silicon carbide FET, the threshold is 5 volts, which is similar to silicon FETs. As a result, there's no need to use any negative gate drive. You can use 0 volts for turn off. And for turn on, you can use 12 volts, because at plus 12 volts, the device is already at its lowest RDS on. So this is really great because it's compatible to the standard silicon gate drive. And also it is compatible with the conventional silicon carbide MOSFET drives. So really you have both choices at hand. And the switching speed you can control by external RG on and RG off. And you can use the snubber to suppress the rating at a minimal energy loss. So At Richardson Electronics, you can find a variety of choices of snubber components. And at the UnitedSiC website down here, here's the link if you would like to learn more about snubber design. And now how about the VGS max rating? So for typical silicon MOSFET or IGBTs, the max rating is usually -20 to +20 volts. But for the conventional silicon carbide MOSFET, the VGS rating is quite limited, especially in the negative side, which is typically -5 to -10 volts. And the reason for this is that the conventional silicon carbide MOSFET threshold tends to drift towards 0 volts if you apply a too negative VGS. So that's why you really cannot exceed this to guarantee its long-term reliability. For the UnitedSiC silicon carbide FET, the VGS rating is ±25 volts, which is similar or even better than silicon devices, and is much better than the conventional silicon carbide MOSFETs. And there's no threshold drift mechanism at all because the gate is made of silicon oxide instead of silicon carbide SiO2. And further, there's a built-in ESD protection diode between the gate and source to enhance its robustness. Okay, so now we have learned about the silicon carbide gate drive guidelines. Let's look at another very important aspect, that's the body diode. So for the conventional silicon carbide MOSFET, the body diode VF is quite high. It's usually about 4.5 volts. And as a result, if you use this body diode for DC conduction, this 4.5 volts is gonna produce a very high DC conduction loss. So as a result, you really have to implement either the synchronized rectification or put a silicon carbide anti-parallel diode next to the MOSFET. So this makes the design more complicated and also adds some cost. And further, some silicon carbide MOSFET body diode even degrades, meaning the VF is getting higher after long-term use. And this was because of the some of the silicon carbide MOSFET, the silicon carbide material defects can cause this if you use the body diode. Now, for the UnitedSiC silicon carbide FET, the body diode VF is 1.5 volts at the rated current. You can see in this figure here. And the knee voltage is only 0.7 volts, very low. And this is similar to silicon MOSFET. So because this VF, body diode VF is so low, you do not need to use synchronized rectification, or you do not need to use any silicon carbide anti-parallel diode. And this simplifies your design and reduces your cost. And this body diode VF does not degrade at all. And this is because this body diode is actually a silicon body diode instead of silicon carbide. And I will show you later on how the reverse conduction works in the following slide. So another very important aspect of the body diode performance is the switching. So what's the QRR during reverse recovery? So let's do a comparison. So this plot here is the reverse recovery switching waveform of a silicon carbide, conventional silicon carbide MOSFET at 150 degrees C. That's the blue curve here. And you can see the QRR is quite high. It's 220 nanocoulomb. And if you are using this silicon carbide MOSFET with a silicon carbide anti-parallel diode, the QRR will go up even further to 275 nanocoulomb. Now, for comparison, the UnitedSiC silicon carbide FET, the QRR is much lower. It's only 105 nanocoulomb. And note this is at 150 C. And this reduction in QRR can reduce the switching loss by a lot. And also note that the UnitedSiC silicon carbide FET QRR only increased about 10% from room temperature to 150 degrees C. So this is very good. So you do not have a switching loss degradation when the temperature goes up. So after looking at the body diode, I would like to compare the two major silicon carbide FET technologies. So this table here on the left is the UnitedSiC silicon carbide FET, and on the right is the conventional silicon carbide MOSFET. So looking at the threshold voltage, the UnitedSiC FET has a threshold voltage of 5 volts, and the conventional silicon carbide MOSFET threshold is quite lower. It's about 2.2 volts typical. And as a result, for gate drive, the UnitedSiC silicon carbide FET, you can use the standard silicon gate drive, which is 0 to 12 volts, or you can use the silicon carbide gate drive of -10 to +20 volts. So both are okay. However, for the conventional silicon carbide MOSFET, a negative -5 volts is a must, and also you have to drive it to high enough voltage, about 20 volts. For the intrinsic body diode, the UnitedSiC silicon carbide FET has a low QRR and only has 10% increase over temperature. But for the conventional silicon carbide MOSFETs, the QRR is much higher, and it increases with temperature about 3 times. And also, it has a high VF, meaning the DC conduction loss is a lot higher. So both types of silicon carbide devices has avalanche capability, and both types have short circuit capability. And the UnitedSiC silicon carbide FET has a stronger short circuit capability. Now let's look inside what's in this UnitedSiC silicon carbide FET. So here is the TO247 package. It has the standard pinout being gate, drain, source. So inside this package, we have packaged 2 chips. One is a silicon carbide JFET chip, which is a high voltage, for example, 1200 volt or 650 volt high voltage chip. And here is a silicon MOSFET chip, which is a low voltage chip, and it does not see high voltage stress. And the 2 chips are connected in this cascade fashion, where you have the JFET source connected to the drain to the silicon MOSFET, these two work together, and from the outside, it works as a normally off FET with the standard pinout GDS. So this is just an example of the TO247 3D package. At UnitedSiC, we also offer a variety of packages, and you can visit this link here to see all the packages we have to offer. So how does this UnitedSiC silicon carbide FET work? So in the on state, during forward conduction, the current simply flow through the JFET channel. The JFET is normally on device, then through the silicon MOSFET channel. So here you apply the VGS of more than 5 volts to turn on the silicon MOSFET, so the current can flow through both chips, and the whole silicon carbide FET is on. In the reverse conduction mode, the silicon FET is off. VGS is 0 volts or negative, so the current will flow through the body diode of the silicon MOSFET, and then it will flow through the channel of the silicon carbide JFET. And because this silicon carbide JFET is a normally on device, so the channel is on, the current can simply flow through both devices. And note that it's flowing through the PN junction inside a silicon MOSFET, and that is why the knee voltage is only 0.7 volts, and there's no body diode degradation mechanism at all. Now, in the off state blocking mode, the VGS is 0 volts or negative, so the silicon MOSFET is turned off. So it will support less than 25 volts, and because the two chips are connected in a cascade fashion, this will be providing a negative 20 volts gate bias to the silicon carbide JFET, and this turns off the silicon carbide JFET, so the JFET can support all the high voltage. And as a result, this silicon MOSFET does not see any high voltage stress during the blocking mode. So after looking at the two different silicon carbide FET technologies, now let's look at where and how can silicon carbide FET be used. So I would like to give you a few case studies. The first case study is a totem pole PFC. It's 85 to 265 AC input, 400 volt DC output, operating at 100 kilohertz in continuous mode CCM. So here's the circuit diagram, and here on the figure here shows the excellent body diode performance. So the blue curve here is the UnitedSiC 650 volt silicon carbide FET. You can see how small the QRR is. It's only 92 nanocoulomb. For comparison, is a silicon superjunction, and this QRR is as high as 6 microcoulomb. So this is the reason why you really cannot use silicon superjunction for this type of CCM totem pole PFC circuits. And here is the efficiency curves of the UnitedSiC 650 volt in this totem pole. For the low line, the efficiency is up to 98.5%, and for the high line, 230 volt AC, we can achieve 99.5% efficiency. So this is really great. And the typical application for this circuit is onboard EV charger, OBC. And we have a lot of customers interested in this device for this particular application. And if you'd like to learn more, you're welcome to visit our website here. This link here, you can find the detailed totem pole reference design, including the BOM list, the circuit diagram, schematics, and the app note about how we design and control the circuit. Okay, so the second case study I would like to show is a high voltage phase shift full bridge. So this circuit is 700 to 800 volt DC input, 40 to 60 volt DC output, and it's a soft switching circuit with a ZVS turn on. So here, it really showcases that the UnitedSiC silicon carbide FET is perfect for soft switching applications. You can see from the efficiency versus output curve, the efficiency is really good, up to 96 to 97%. And with this high output voltage, you can use a full bridge Schottky diode rectifier to get the lowest loss. So this circuit is very good for on or off-board EV charger, or it can be used for onboard DC-DC. And again, down here is the link if you would like to learn more about this high voltage phase shift full bridge reference design. Okay, so next I would like to talk about upgrading your existing design with drop-in replacement solution. So here are a few cases. So first, your current solution might be a conventional silicon carbide MOSFET. So you already implemented the -5 volts to +20 volts gate drive. So the UnitedSiC solution would be, you can just use the UnitedSiC silicon carbide FET as a drop-in replacement because the gate drive of -5 to +20 volts also works. And the benefit would be you can achieve better or same efficiency. And the tip I would like to give you is you might want to adjust the RG on or RG off to achieve your desired switching speed, because the UnitedSiC silicon carbide FET is a very fast switching device. Then if you're using silicon 1200 volt MOSFETs, then the UnitedSiC 1200 volt silicon carbide FET can serve as a replacement. And again, it will boost efficiency, and it's fully compatible with silicon MOSFET gate drive. If you are using silicon high-speed IGBTs, then the UnitedSiC silicon carbide FET can serve as a replacement for the IGBT plus FRD co-pack. And again, it will boost your efficiency. And since UnitedSiC FET switches much faster, so it depends on your current circuit layout. So you might need to relay out your circuit to reduce the parasitics. But worth pointing out is there will be no problem with short circuit capability, even if you're using a high gate bias. And lastly, your current solution might be a silicon-based high-speed superjunction MOSFET. Then UnitedSiC offer a 650 volt class silicon carbide FET can serve as a replacement for the superjunction MOSFET. And again, it will boost efficiency, and it has similar COSS, but much lower EOSS. And also, it has much better diode QRR. So this enables, for example, the CCM mode totem pole application, which the silicon superjunction MOSFET cannot do. So here's a case study of a drop-in replacement for silicon superjunction MOSFET. So this is a phase shift full bridge soft switching circuit. So it was using a 40 medium 650 volt silicon superjunction, and which was replaced by the UnitedSiC 650 volt silicon carbide FET. So here from the efficiency curves, you can see there's a boost in efficiency across the whole output power range. So this is really great because a lot of users, for example, in the server power applications, really cares about the efficiency not only at full load, but also at mid and light load. Another benefit you can see here from the switching waveforms is the silicon superjunction MOSFET has a much longer delay due to the CISS. But after replacing it with the UnitedSiC silicon carbide FET, the delay is much lower, and so this means you can do much faster switching due to this greatly reduced capacitance. So now I've gave you the 5 design tips, and at UnitedSiC we offer a whole variety of devices to help with your design. We have the Schottky diodes, silicon carbide Schottky diodes, the standalone silicon carbide JFETs, and the silicon carbide FETs, which comes in the 2 categories: the UJ3C series for the soft switching, and the UF3C that's more optimized towards hard switching. They come at 650 volt class and 1200 volt class with very low RDS(on) and great body diode performances. For the package-wise, we have the standard TO220, D2 pack, D-pack, and the TO2473 lead. They all have the standard GTS pinout. Also, we have the 4-lead TO247, which is in production and in stock at Richardson. And we also have the 7-lead D2 pack. The samples are available now, and we expect full production and stocking by next quarter. And again, if you would like to learn more about our product lineup, you can visit the link below here. So where to buy? Richardson Electronics is our global supplier of UnitedSiC products, and here is their website. And if you would like to find more information, you're welcome to visit UnitedSiC website, UnitedSiC.com, where you can find the datasheet and SPICE models, app notes and white papers, and our technical blogs, and also our very comprehensive product selector guide, and also the demo boards and reference designs, including the circuit schematics, the BOM list, and also the app notes. Okay, so next, I would like to answer a few questions. So we have already got a few questions. The first one is, why does UnitedSiC's and carbide FETs QRR only increase so little over temperature, which is about 10% from 25C to 150C? So this is because for UnitedSiC's and carbide FET, most of the QRR comes from the capacitive charge of the silicon carbide JFET COSS. And since it's a capacitive charge, it does not increase with temperature. A very small portion of the QRR does come from the low voltage silicon MOSFET body diode, and that portion does increase with temperature. So overall, combining the two, that's why you have about 10% QRR increase, which is still very small. The second question is, in the datasheet, you recommended using a large RG of 20 ohms for turnoff. Why is that? Okay, so this is because the UnitedSiC silicon carbide FET has a very small CGD, so it tends to turn off very fast. It's a very fast switching device, which also gives you very low turn-off loss. And what we have found is using about 20 ohms RG off, you can slow down the turn-off dP/dt to the desirable level, which is about 80 volt per nanosecond, which is still quite fast and gives you very low turn-off loss. So basically, you can achieve the same or better turn-off loss as the conventional silicon carbide MOSFETs using this 20 ohm RG off. For the third question is, on slide 26, what is the reason for the big efficiency improvement at light load? Okay, so let's go back to slide 26. Okay, here. Okay, so this is the drop-in replacement of a silicon superjunction. So here you see this improvement of the efficiency. So because this circuit is a phase shift for bridge, it means that it's a soft turn on. There's very low or no E on loss. All the loss is turn off loss and the conduction loss. So at high load, this loss is the combination of the conduction loss and the turn off loss. Now at light load, because the device barely conducts or only conducts for a very short period of time, so the conduction loss is quite low, and this loss is dominated by the turn off loss. And because the UnitedSiC FET has much lower EOSS than the silicon superjunction, so the turn-off loss is much lower. That's why you see this big efficiency improvement at light load. And this is very important for example, for power server applications, where the goal is to really to improve the efficiency, not only here at high load, but also at mid load and light load, because the server operates at all different loads throughout its lifetime. So due to time restraints, I cannot answer more all the questions. So if you have more questions, please feel free to email us at sales@unitedsic.com. And again, on behalf of Richardson Electronics and the UnitedSiC, I would like to thank everyone for attending today's webinar. Thank you very much. Goodbye.